In this video, I'm going to look at box models and how we solve them using numerical integration techniques. So how we set them up and how we solve them. And so the first example I want to do is a very simple one that you can just almost solve in your head. We imagine we have a basin like a bathtub, a reservoir, and this will be our box. And we have an inflow of water into it, and the water flows into the tub at a certain rate, R, and the volume of water in the tub is V. And what we're trying to do is find out what is V as a function of time. So let me define the variables here. R, which is going to be a function of T, is the flow in, and the dimensions of R is going to be in a volume, L cubed per unit time. And then the volume V, which is the variable we want to know, is the volume of water. And its dimensions is in length cubed. And so to set up the model, what we do is we use the idea of conservation of the volume of water. So water is neither destroyed nor created, and therefore the rate of change of V, which is the derivative dV dt, is equal to the flow in minus the flow out. In this simple example, we have a source in but no flow out, so this is just equal to R, the rate of flow in. And we can check the dimensions, make sure that everything is dimensionally correct, right? The left-hand side, right? The dimensions of the left-hand side, dV dt, is equal to the dimensions of dV divided by the dimensions of dt, which is equal to a length cubed over a time. Whereas the right-hand side, remember our right-hand side is just a length cubed divided by time. So this is indeed dimensionally correct. And this equation is easy to solve. The way we would solve it in this case, we just integrate both sides of the equation. So to do the integral, what we want to do, we need what's called an initial condition, which is the volume at some prescribed time. And here we're going to pick that to be at t0. So the initial condition is going to be that V at time 0 is equal to 0. We're going to we assume the tank is empty, and then it starts filling up. So if we integrate the equation from both sides, we get the integral from time 0 to some time tau dV dt is equal to the integral from 0 to tau of R dt. And if we assume that the rate of flow in is a constant, so we're going to assume here, assuming R is constant, just to make our life easy, then the right-hand side is just R times tau minus 0, and the left-hand side, if we're integrating the derivative, we just get back the original function. So we get V evaluated at tau and 0, and so we have V at tau minus V at 0 is equal to R times tau, or V of tau is equal to R times tau, where we use the initial condition, right? You see how when we did the integral, the initial condition came up and that was 0, so we get the final solution. And if I graph the solution, it's going to be simple. We have V of tau, and we have tau. If this is tau equals to 0 at this time, then the graph it just increases at a rate R. So the slope here, the rise over the run, so delta V over delta tau is equal to R. So the slope is just R. And I guess this little picture with the little delta V over delta R is the motivation for how we are going to solve the equation numerically. So what we're going to do is we're going to break up time into discrete time intervals, and we're going to just sum the total flow rate between each integral to get what the volume is as a function of time. So let me point out how we would do it. So the numerical method of solving it, and we're going to use a method called Euler forward integration. And why it's forward will become apparent lately. For now, just use it as a name. All right, so the equation we want is this one, dv d tau, or dv dt, sorry, is equal to r, and v at 0 is equal to 0. So this is the equation we want to solve. And instead of, if on a computer, what we will do is we will go back to the definition of the derivative, which you remember is this one, dv dt is equal to the limit as h goes to 0 at v at t plus h minus v at t divided by h. And if what we'll do for the numerical solution is we're not going to take the limit. We're going to pick h to be small, but not 0. And so that we're going to have what's called a finite difference. We're going to go from 1 time t to t plus h, and we're going to pick a small h, but not infinitesimal. So we'll pick h to be equal to dt to be finite, to be small but finite. And then the equation then becomes v at times t plus dt minus v at times t divided by dt is equal to r. And then it's just a matter of doing some algebra. What we get is v at times t plus dt is equal to v at times t plus r times dt. And if this is kind of a recursion expression. If we know v at times t, we can get it the next time by just using this expression. So if we start at the initial condition with v of 0 equals 0, then we can get v at dt will be v at 0 plus r times dt is just r dt. And then at the next time step at 2 dt is going to be v at dt plus r dt will be r dt plus r dt is equal to 2r dt. And then v at 3 dt is v at 2 dt plus r dt is equal to 2r dt plus r dt is equal to 3r dt. And you can easily see what happens as a function of time. In this case, we can do the numerical integration in our head. We don't need a computer even, because the solution is very simple. The general solution is v of n dt is just equal to n times r times dt for n equals 0, 1, 2, and so on. So in this case, because the example is so simple, we don't even need the computer to solve it. But we will use the computer to set it up just so you can know how to code it before we add more complexity to our model. So let's go to the computer. And this will be the bathtub filling problem. All right, so we need to specify numbers, and we need a number for r. So let's pretend that r is equal to, let's say, 0.1, maybe 0.1 meters cubed per second. That's a lot. Let's assume it's 1 liter per second. So that would be another 0 over here, right? There's 1,000 liters in a cubic meter. So this is roughly a liter per second, which is a fast flow rate, but not impossibly fast. And then we need to specify the initial condition. So initial condition, which is t is equal to 0 and v is equal to 0. And then what we will decide is how long we want to integrate the model. So let's say the duration of the integration, and t is going to be, let's pick a number of times, let's say 2 minutes. So in 2 minutes, that's 120 seconds. And so the number of time steps, n, is going to be t divided by delta t plus 1. All right, so we did pick a delta t, which is our time step. And let's choose dt to be 1 second. And so why do I add the 1? Well, it's because of it's kind of a fence post thing. If this is t equal to 0, and over here I have t equals to 120 seconds, and suppose I divide the time interval into 3. So I have 1, 2. So I have 1 interval, 2 interval, 3 interval. So these are all delta t, and delta t. So I have 3 time steps, so I'll start from here and I'll step to this time, then I'll use the solution here and step to the next time, and then I'll step to the next time. I have 3 time steps, but I have 1, 2, 3, 4 times at which I have 4 discrete times when I have the solution, starting with the initial time. So that's why I added the 1 over here. And so the volume, I'm going to initialize it to be just zeros of n comma 1. And I suppose I'm going to move the initial conditions to afterwards here. So maybe what I should do is have this here and just make this nans. So nan. So right now the v is not defined, it's going to be all nans. And then I'm going to reassign v1 to be 0. So that's the initial condition. So the first snapshot is going to correspond to n equals 0, the initial time. And then I can time step 2, 4, k equals 1, or maybe I could use a little n since that's what I was using over here. For n equals 2 all the way up to big N. And then v of k, m, sorry, I wanted to use little m, is equal to v at n minus 1 plus dt times r. End. So you can see that when I go through the for loop, I'm going to assign, I already know what v1 is. So when n is equal to 2, then 2 minus 1 is 1. v1 is already known as 0, and then I can compute v at 2. And then the next time I go through the loop, I can determine v at step 3, 4, 5, 6, and so on all the way up to n. And then I could finally plot the solution. So maybe I should increase the time variable. So let me also have a time variable. Tau is equal to nans, and then tau of 1 is equal to t. And here, tau of n is equal to tau of n minus 1 plus dt. And then we can make a plot. So plot tau v in red, set tc. Let's put it in black. And then label the axis. All right, let's run it. Oh, I forgot to put the semicolons on the tau. And this is the solution, which in this case is the exact solution. And so even though I did finite differences, it turns out that the answer is exactly the same if we had just plotted the analytical solution, which we had before, which is just r times tau. Now we will see then when we do more complicated problems, it will not be the case that the discrete solution is exactly equal to the analytical solution. There will be some errors that come in from the act of not taking the limit when we define the derivative. But you can see the volume is increasing linearly and the rate of increase is r, so we can check that that's correct. So over the full time span, right, delta t is equal to 120 seconds, and the change in volume is 0.12, so delta v is equal to 0.12 meters cubed. And so the rate r, we're checking, should be delta v over delta t. And since r is a constant, and you see that the slope is a constant through the whole integration, that's 0.12 divided by 120, which is equal to 10 to the minus 1, 2, 3, 10 to the minus 3, which I think is what I picked. Yes, r is 10 to the minus 3. R, and this is as units, right? It's meters cubed per second. All right, so that's the first example.